Purpose of this video is to provide you with an additional resource for electric field vector addition. This is probably the first real substantial topic that we encounter in class, and so I wanted you to have more resources at your disposal for this. So we're going to walk through a situation that considers 2 point charges and look at some different aspects of this, and you will have this for your reference. So the situation specifically that we're considering are 2 point charges, Q1 and Q2, lying on the x-axis. And the first thing that we're going to look at is just to sketch what the electric field would look like. So let's do that. Now the charges are not equal. They are different magnitudes and different signs. So Q1 is -1 microcoulomb, and Q2 is 3 microcoulomb. And so we know how electric field lines look generally. They point from positive to negative, so there would be a line that would be pointing from Q2 to Q1, and then we could draw, more field lines that point into Q1 and out of Q2. Now, if we're trying to be a little bit quantitative, there should be 3 times as many field lines emanating from Q2 as going into Q1, because Q2 is 3 times the magnitude. So we should have about something like this, like 9 going out versus 3 going in. And we could flesh this out. We could add some. This configuration is basically a dipole where the 2 charges are not the same size. So, it's going to look something like, roughly like this. Again, these electric field diagrams are not particularly quantitative, but it gives us an idea of what the configuration looks like. So something like that. Now, the next thing that we want to do is actually find the magnitude and direction of the electric field at the spot exactly between the 2 charges. So let's draw our cartoon again, Q1 and Q2. And just so we have it here, Q1 was -1 microcoulomb. Q2 was 3 microcoulomb. Let's see, the distance between these are separated by a distance of 10 centimeters. And so what is this going to look like? We want to write an expression for the electric field at this point in between, and which we called A. And we're also going to actually calculate what the value of that would be based on these charge values and distance. And then we'll also come up with what the force on a charge placed at that location would be. So to find the electric field, we can think of this as there's going to be 2 contributions. There would be a contribution from Q1, maybe call this one E1, and then there would also be a contribution from Q2. Call that one Q2. Now they're pointing in the same direction, because since Q1 is negative, E1 would point towards it, and since Q2 is positive, E2 would point away from it and towards Q1. So what's this going to look like? E1 plus E2. And what are those in terms of the information that we have? So this would look like K Q1 over, now the distance to the middle would be half of D, so let's just write that in as D over 2. And what direction is that? That's going in the negative x direction, so negative I hat. And then the other contribution would be K Q2 D over 2 squared, also in the same direction. So notice we could consolidate this a little and pull out all the stuff that's the same. And we're left with Q1 plus Q2. Now, bear in mind, these are just the magnitudes. If you want to think about it as we've accounted for the direction information already, so we don't want to double count this negative sign on Q1. So I'll just write it like this to make it very clear that we've already counted that. And this is all pointing in the negative I hat direction. And so this would be an expression for the net electric field. And then we could actually compute a value for this as well. We know K is 1 over 4 pi epsilon naught. Our factor of d over 2 would be, I'll just put it all in here. So this would be, 0.1 meters. Let's just call this 0.05 meters squared. And then our charges would be 3 plus 1 microcoulomb, so 4 microcoulomb. And if we actually compute what this is, we would get that the numerical value for this is 1.4 times 10 to the 7 newtons per coulomb in the negative I direction. That's the numerical value. Now, the last bit of this question asks us, if we were to place a charge of Q equals negative 1 microcoulomb at that location, what would the force be? Well, the force, remember, this gets at the definition of electric field. So electric field is force per Q. So the force then is E times Q. So we could compute this as our 1.4. And actually, we can put all the ingredients together, 1.4 times 10 to the 7 newtons per coulomb, times our charge of negative 1 microcoulombs. And what is this going to give us? 14, basically multiplying 10 to the 7 times 10 to the minus 6. So we'll be left over, we'll have 14 newtons per coulomb, newtons left over. And what direction is this pointing in? Well, notice this is now negative I hat. This would be pointing in I hat. And does this make sense? Hopefully, because if the electric field was pointing like this, and you put a negative charge on it, the force on that charge is going to be, in the opposite direction to the electric field line. So the force would point in the positive I hat direction. Cool. So this is a real simple one-dimensional vector addition situation. So let's build on this. So the next part of the question asks us to reason out where on the x-axis the electric field goes away. So where is it 0? And we can see that. Let's draw some cartoons to try and figure that out. So this Q1 is negative, and then Q2 over here we know is positive. And so what we'll do is let me try and color code this in red and blue. So let's make Q1 red. So we know that the electric field lines for Q1 point towards it because it is negative. So what I'm going to do is just draw an arrow everywhere to kind of indicate that. And notice I'll draw the arrow shorter when it's farther away because we know that the electric field goes like 1 over r squared. And then let's make Q2 blue. So for Q2, we know the electric field lines point away from Q2. And for the same distance, we're going to make them longer to indicate that the electric field from Q2 is stronger because Q2 is 3 times larger than Q1. And so what does that mean? Well, we'll end up with a cartoon that looks like this. So notice that in between they're pointing in the same direction, so they can't cancel there. To the right, they're pointing in opposite directions, but since we're closer to Q2 and Q2 is larger, it's going to be impossible for Q1 to cancel out Q2. And so the only place where these can actually cancel each other is going to be over here, so to the left. And we can figure out actually exactly where that is if we do a little algebra. So let's say that the distance between them is d, and this distance beyond Q1 is d2. So what does it mean when they cancel? Well, the magnitude of those two electric fields is going to have to be the same. So in other words, K, so at this location, E1 is going to have to equal E2. So to cancel, so what does that look like? Well, that means KQ1, and the distance that we're talking about in terms of our cartoon is D2 squared, is going to have to be equal to KQ2 over D2 plus D squared. So that's our condition. So basically what we need to do is then solve for D2. So notice some of the stuff is going to drop out, like K is going to drop out. Again, we're actually talking about the magnitudes here, so let me just make that explicit by saying, putting some bars in there. And let's substitute in the fact that we know that Q2 is just 3 Q1. So let's put that in and see what the effect of that is. So Q1 over D2 squared, and then we'll expand on the other side. So we have 3 Q1 over D2 squared plus 2 D2D plus D squared. So we can get rid of the factor of Q. And then let's multiply across so we can get everything upstairs. So we would have D2 squared plus 2 D2D plus D squared equals D2 squared. And then notice we could then subtract the factor of D2 squared from both sides. And then we're left with this expression. Oh, wait a second, I forgot my factor of 3. Sorry. So we would have 3. We can't just subtract. Hold up. This would be 3 D2 squared. So we're not going to be able to get rid of it, but we can, combine these two pieces together. And what would we be left with? We're going to have, let's put it all on the same side. So we would have negative 2 D2 squared plus 2 D2D plus D squared equals 0. Notice this is an expression that has a D2 squared term, a D2 term, and a constant. So in other words, it's a quadratic. And so I'm not going to show solving the quadratic, but you take, take this and plug it into your quadratic formula, or whatever, however you normally solve your quadratics, and you would find that D2 equals 0.137. So this is just kind of an interesting, the exact number isn't so interesting, more just to reason out where the electric field would cancel. Okay, so the next part of this is really the part that I wanted to focus on for you, and because this will be vector addition in 2 dimensions, and this is the more, the more complicated task. So let me paste our diagram from above in here so we can just have it for a reference, because we're gonna want it in this case. Okay, we need to find now the magnitude and direction of the E field at B. So before, we found it at A already, and now we're interested in what's happening here. And what is that going to look like? Well, qualitatively, we know we're going to have an electric field due to Q1 that would point like this. Maybe we call this guy E1. And then we would have pointing towards it because it's negative. And then we would have a contribution that would be pointing like this. Due to E2, due to Q2 because Q2 is positive, so it would be pointing directly up. And then, the E net at B is just E1 plus E2 in my cartoon. And so we need to work out what those two contributions are and then add them up. So what is E1? So E1, well, we know that all these are going to look like KQ over R squared times R hat. So in this case, what is it going to be? We're going to have K Q1 over R. What's R in this case? So it's the hypotenuse of this triangle. This is D, this is D. This must be root 2 D. So this would be root 2 D quantity squared. And then this, the direction that this is pointing, it's pointing down 1 unit and over 1 unit. And so we can write the unit vector. So there's different ways that you could do this, right? You could do it by breaking it into components. Let's do this first by using the unit vector. So what is the unit vector? Let me call this specifically R1 hat. So what is R1 hat? R1 hat is the unit vector that points in the direction of R1. So for us, R1 would be the vector that points from B to Q1. We're incorporating the sign information of that negative charge, recognizing that that vector would point towards it. And so what is R1? Well, R1 hat would be R1, which is D in the negative I hat plus D in the negative J hat divided by root 2 times D. And so we can cancel out that factor of D that appears everywhere. And notice then that this unit vector would be negative I hat minus J hat over root 2. So unit vectors themselves have lengths of 1, so this is 1 squared plus 1 squared square root over root 2 has a magnitude of 1. So this is the unit vector R1 hat. Okay, so this is E1. E2 is simpler because it's just pointed in the positive, y in the j hat direction. So what does this look like? This just looks like Q2 over the distance in this case is just d squared, or sorry, d, and then we square it. And then R2 hat is just j. So this would look like Q2 over d squared j hat. So that's E2. And so the other thing that we probably want to put into here is, well, we can do it later. We also know the fact that Q2 is 3 times Q1. So again, we've already incorporated the sign information in our cartoon. So we can add this piece of information in when we add them together, or we could also add it here. So why don't we just do both. We'll do 3q1 squared. All right. Okay, so let's add these together then. So E net at B is E1 plus 2. And what are our contributions? So up here we have KQ1 over 2D squared times I hat minus J hat over root 2. And then from E2, we're going to have 3Q1 J hat over D squared. Okay, so we can collect the pieces or that have this, that are pointed in the same direction. So these two J hat contributions would be combined together. So, and we could, oh, I left out, oh, hold up a second. There's a factor of K that's omitted. So we could factor out, notice the K, the Q1, the D squared, and simplify this a little bit. So you'd have K Q1 over D squared times negative I hat over 2 root 2 plus, let's see, so we're going to have 3 J hat and then minus J hat over 2 root 2. So that's a pretty compact, about as compact as you would be able to write E net. Notice though, it asks us for both the magnitude and the direction. So if I was asking you just for an expression for the electric field, this would be sufficient. I guess we could factor out this J hat. We could clean this up ever so slightly to make it a little bit more compact, but you get the idea. But we're after the magnitude and the direction, so actually we would need to compute those two parts. So we have values for all of these charges. So we know that Q1 was what was Q1? 1 microcoulomb. And the rest of this, notice, is just numerical factors, constants, etc. So the D is 10 centimeters, etc. So actually, here, let me just write out what it would be, just so you can see it. But if we wanted to compute these as numerical values, you have your 1 over 4 pi epsilon naught. We could put this in as a number even. 12, 10 to the minus 12. 1 over, so our charge would be 1 10 to the minus 6. Let's see, 2 over root 2. So all I'm trying to say here is that you can put in, all your numbers and compute what these values would be, and you'd find that this would be negative 3.18 times 10 to the 5th newtons per coulomb in I hat, and positive 2.37 times 10 to the 6th newtons per coulomb in J hat. Okay. So in order to get the magnitude, the magnitude of this, we would have to square EX and EY and add them together and take a square root. So conceptually, it would be this. The two components, the X part and the Y part. So you could do that from these numbers. You could take the two numbers and get that. This isn't particularly exciting. You get the idea. And, conceptually, you can see that the Y part is bigger, so it's probably unsurprising that when you do that, you would find that this is approximately 2.4. So in other words, it's pointed mostly in the Y direction and a little bit in the negative X direction. So, and this is useful context to figure out the direction. So it looks kind of like this. So to get the direction, well, for that you would use, arctangent. Let's do it in a couple steps. So something like this, tangent theta is going to be E y over EX. And so you would just look at the ratio of those to say, okay, theta is going to be inverse tangent of EY over EX. So what is that? So that would be 2.376 over et cetera, et cetera. Not super exciting, but we find in this case that this is 82 degrees, which relative to the negative x-axis. So, which is reasonable. We know that it's going up a lot more than it is going in the negative x direction. So, you could also do this same kind of problem without using the unit vector, but with using components, in which case we would have to figure out what the angles are. So it would be, let me just put a note here. So you could also do this with components. The electric field due to Q2 would be the same because it's just along the y-axis. But we would need to figure out, for the other one, for E1, you could imagine like writing theta like that or something. So maybe just to give you a flavor for that, think of it as like, we know it's pointing like this. Theta's here. So we could figure out E1x would be basically, k q1 over the distance and everything is the same, root 2d squared times a factor of cosine theta, and we know that that would be in the negative I hat direction. And cosine theta, notice the thing was square, so that theta was 45 degrees. So this would equal cosine 45 degrees is root 2 over 2, which is 1 over root 2. So in other words, this is the exact same thing that you would see with that we saw with the using the unit vector itself. So it's just another route. If you're more comfortable with working with angles, then do the components. If you're more comfortable with working with the unit vector, then, or if you find that way useful, then do it that way. So, and you could see E1y would be the same thing. This would be k q1 root 2 over d squared times, in this case, it'd be sine component, right? You would want the sine piece. And what's sine of 45 degrees but 1 over root 2? So you would end up in exactly the same place. So, and then the last little bit on here is how would this problem be different if instead of point charges we were working with two infinite wires that were spaced like that? Basically, you would want to be able to do this same kind of problem. The only qualitative difference is that instead of, the point, so basically, if you consider like two wires that were coming at you, could you find the field above here? It'd be the same kind of problem, except instead of being, behaving like kq over r squared, it would be lambda over 2 pi epsilon naught r. So behavior-wise, the only thing that's different is it behaves like 1 over r instead of 1 over r squared. The steps, adding together the vectors, all of that are exactly the same kind of task.